Bismillahirrahmanirrahim. I'm Fatima Tayyab from fifth semester mechatronics engineering, and it is my lab task of microcontroller and embedded system. Uh, so in our first lab, we had learned about different softwares and how to download them and how to write code in Atmos Studio in assembly language and in C language, and how to build them and debug them, and how to generate their hex files. And also we had studied how to use Arduino IDE software and how to upload the code on microcontroller. We can use the microcontroller of our own choice. We can also take Arduino Uno 328B or Arduino Mega 2560. So in our first task, we had studied about our blink test. First, we had upload the assembly language code, which is uploaded, which had already uploaded in a microcontroller, and now I'm running the simulation. And this is our blink test for assembly language. Now moving towards our next task, which is uploading of C language code in Arduino Mega 328B. Now I'm running the simulation. The blink test of C language is this, where the speed of blink for assembly language is greater than C language. And then it is a simple example from Proteus, which is the blink test from Arduino IDE hex file. And this is the blink test for the Arduino IDE example from blink test. It is just simply a basic lab to learn about the basics of how to write code, how to implement them on Arduino on our examples. Now moving towards our next lab, which is lab number 2, an introduction and implementation of assembly language or programming on 80 MHz to 8P. So in this lab, basically we had learned about different assembly language codes, and our first task is to storing the value of store the value 30 in R16 register in binary and display it on any port. After then, we have to add 25 in that value of that value, which is R16 register, and then this value will be shown into any port, and then in the end we have to clear the R16. Here we have stored the 0x1e, which is the hex of 30, and store it in register R16. And then we have to add this value to the show this value to the output port B, and then we have stored 25, uh, uh, which is the decimal of 0x19 in R17, and then with add command we had added R17 to R16, and this value will be stored in R16 register, which is then display on the port B, and then the CLR command will be used to clear the R16 port, and then we will move towards the over next task, which is to take an input from one port and display it on other. When we give the display in this port, which is port B, we will see over output on port C. This is the simulation of this task, and I had already uploaded the next file in this microcontroller, and moving towards its code. It is this its code. In this first we have stored 0 value to R16 register, and then store 0xff in R17 register, and with this we had displaying the value of port B. And here we had used this R16 register to make the port B as input and making the port C as output. And in this, we have making the R pin B uh, to store the value of R pin B in R18 register, and and then its value to port C, which will be the output, and with the jump command, it will again and again run this part of the code. Now moving towards our next task, which is to display the charging sequence of LEDs on any port. It is the code in which we actually toggle the ports with the LDI R19 0xF, but we have stored the value of 0xF to R19 register and then making it at output. With SCI command, we are setting the bit 0 of port B, and then delay will be called, and then again we clear the port 0 of port B. The CBI command is actually used to clear the port, and this process will be continue for all the ports of port B, and this will this loop will continue, and this is the delay function which we had used, and moving towards its simulation. I had already uploaded the code in this microcontroller, and this is the charging and discharging of the LEDs. And then moving towards our task number 4, which which is to take the values. If the values are same for both the ports, port B and port C, then it will be show the value of 1100 and if not if these values are not equal, then this will show 0011 I had already uploaded the code, and the results are as shown, and the code is here. Firstly, we had stored the zero value to R16, and then making the ports as a input. DDR data direction register B and data direction register C are used to making the port as input, and then port D is taking as an output, and then from start there is a loop in which we had produced different conditions. If branches are equal, then the result of 0011 will be shown at port B, and if not equal, and then this will be shown. It will if these branches are equal, then this will jump towards this code, and if this condition is not true, this will only implement this part of the code. Now moving towards our next task, which is just simply to show the use of command sts jump move out sub in decrement and comb. Here 30 will be stored in R16, and comb will show the uh, complement of R16, and then there is an increment of R16 register, and then 40 will be added to the R17, and then there is a decrement in R17 by value of 1, and then mm, by add command R17 will be added into R16, and then with move command R17 value will be moving towards R16. That means copy of R17 value to R16. With STS command, the R16 value will be stored in the 0x600 address, and with subcommand R17 value will be subtracted from R16 value, and with the jump L1 it will again jump to L1. Noted, it is an unconditional jump. Now I'm moving toward my third lab, which is Introduction and Implementation of C Programming on 80 MHz 328p, and it's interfacing with 7-segment display and hex keypad. Before starting this lab, I'll tell you some benefits of C programming. It is much easier and less time consuming to write code in C than in assembly, and C is easier to modify and update. We can use the code available in function libraries, and also C code is portable than other microcontrollers with little or no modifications. So it is our 7-segment display. We have to concern datasheet before the connections of before it's interfacing with Arduino Mega or any other microcontroller. Our source code has already written. We can also edit on Atmel Studio or any other file. In this task, we had basically make a counter from 0 to 99 with any delay. So we had called the delay function with 150 milliseconds of delay, and at port D we had shown our value of Z, which was started from 0 and ended at 99. Now I'm running the simulation. It is not accurately working. Now I'm moving towards my second task. There are several other tasks which we had provided. This is to toggle the bits whenever switch is open. It will show the values on D2, D4, D6, and D8, and when it is closed, it will toggle the bits. In this, we had replaced the over switch with a logic state, and then moving towards over. It is and then moving towards our next task, which is the interfacing of a hex keypad with the 7-segment display. When I press 4, 4 will be shown on the 7-segment display. In actual 7-segment display has 7 entities placed near it, and in hex keypad we have 4 rows and 4 columns which are interconnected with each other. We had also implemented 7-segment bus switches, but here I will only show you the actual 7-segment which is available in Proteus, or it is also available in our lab. So when I press 5, 5 will be shown in the 7-segment display. So moving towards our next lab, I had skipped the code of hex keypad interfacing with 7 segment display. So in its code, we had first initializes the pull-up registers on AVR pin PD2, and then data direction registers of port B are being triggered to 1, and then we had initializes an array of x8, which will be then used in our loops. And from these conditions, when we will press a certain button, a certain LED will be on, and so on. Now moving towards our lab 4, which is the introduction and interfacing of LCD with hex keypad and a microcontroller. So before interfacing of this, we should have to see their data sheets to see what are the connections should be made with the microcontroller. And with this, I had already uploaded its hex file in microcontroller. We'll see the result. Now moving towards its code. It is its main code in which we have first defined the uh, pins of LCD. In D0 is connected with the PC0, and D1 connected with PC2. These all the pins are connected with the port C of our microcontroller, and RS RW and enable pin are is connected with PD0, PD1, PD4, which is over port D, and these are the header files which we had used. And in int main, we had first initializes the pull-up registers on AVR pin, and then data direction registers of port P are one to enable the output. And then over then we had write an array for which is stored in x7, and character a is used. So in this LCD command is used when we press a certain button. First the cursor will shift to the to position right, and after this over port B is initializes with the value which we have stored with the in the LCD initialize command, which is used to write value on LCD, while one loop is forever loop, which will never break. And with this, when we press 1, LCD data will show the value of 1 to the display, and when we press 2, the data will be write in the value of 2, and so on. These are interconnected with the rows and columns of hex keypad, which had already written in our code, and there is also another code in overlap for which is used to show the sentence hello world on the display of LCD, which is written as this where RSRW and enable pins are connected with port B, PB0, PB1, PB2, and these are the header under functions. And in this we had write different commands to initialize the LCD, to clear LCD, to move the to make cursor on, and um, to write. And then with delay of 1 second, there is a pause. There is a pause, and with LCD command, there are certain functions are used, and to write data, we have this function. There are several other functions which can also added in that, but in this we had just write the right shift, left shift of cursor, and also the LCD data strings. to write the hello world on the LCD. In this, over the port C has been written as the output port, and DDRB, which is over the data direction register for port B, where our value is given. Now moving towards our next lab, which is lab number 5, and in this we have studied about the implementation of timers, counters, PWM on ATmega 328P using Advanced Studio and Proteus. We have given with the different types of timers, which are timer 0, timer 1, timer 2, in which timer 0 and timer 2 are 8-bit, and timer 1 is 16-bit. And our first task is to display the counting on TC&T register on LCD, and also counting how many times the TC&T counter is overflowing and showing it on LCD. So here TOV shows that how many times the timer overflow, and TC&T FF is shown its counting. And its code is this, where first we had to write the header files for the header file for LCD, which I had already explained. And here is its main code, where CPU is defining its crystal value. And in the main code, first we had um, call the LCD initialize function, which has already written in our header file, and then we are making the port D bit 5 as an input, and DDRC 0 as output. So first we have TC&T value, which is a timer counter registered, and its value is initially as 0, and then making the TCCR counter control register as 0, and which it is actually in series mode, and and counter for the final S triggered. And this is the loop for which if our timer overflow TOV register is 1, then it will be shown the value on the LCD, which is in our case has a change 1, and then I had paused the simulation to show its value. And our next task is to make digital watch using timers on the LCD or 7-segment display. So here is our second task, which is used as a timer. So here is minutes, seconds, and then it shows timer. So in its code, we had initialize the hour, minute, seconds, and there is another function which is called check, which is then count variable when count one is it is count when 1 second of delay is halt. And here is the function which shows the value of timer on the LCD, which is written as LCD clock, and so on. Actually, this command is used to display the number, that means time in hour, minute, and second on LCD, and in the else condition, uh, this A0x30 is used to convert the number in hex, and where A is equals to 8 divided by 10 is used to remove the last digit, and this LCD data write B, here the value of this B is stored which will be later shown to LCD. And here timer 1 to initialize the timer 1, and this condition is used to operate the CTC mode of timer 1. And this condition is defined as no pre-scaling condition. And in this we had initializing the timer 1 interrupt, and the SA command is used to enable the global interrupt bit when time mask is initializing the initializing interrupt for the timer 1A register. And this function is to is for timer 1 interrupt subroutine to control the variables of a clock where check 1 is incrementing the values of it. Then in this function we will first initialize the LCD, then instructs the then we had instructs to set the time on LCD, and then there is a delay of 1000 milliseconds, and then LCD will be clear, as we had already seen in the over simulation. And then again there is a delay of 10 seconds, 10 milliseconds, and then over a function of timer one interrupt is called to initialize the timer one interrupt, and then again we had initializes the timer 1, and then we had value calculation the value for 1 millisecond, and starts the timer again, where while 1 is an infinite loop to display time continuously. And this LGD end jump is used to display the address of second, where we have stored the second command, and this is used to write the minute, and this command is used to write the hour. Now moving towards over to sixth lab. In the first part, we will first discuss the SPI, which is serial peripheral interfacing. Basically, SPI is asynchronous full duplex master-slave based interface. Data from the master or the slave is synchronized on the rising or falling edge clock edge. Both master and slave can transmit data at the same time. The SPI interface can be either 3-wire or a 4-wire. We had used over. Um, Here is my code, in which first we had to include 300 files, and here MISO means master in, slave out at 4 pin. In main, we had to first connected the LCD with over master, in which over port D is um, port B have master in, slave out pin, which will be 1, and SPE will be 1. And in while loop, we had write the data which we had taken from the microcontroller, and then it is the code for the slave, in which we had connected a hex keypad, which will take an value from row and column in column interfacing of it, and here the MOSI, master out, slave in, master in, slave out, and slave select commands are connected, are at in 3, 5, and 2, and with send data command character U is taken, and in this we had the value obtaining from the port D, which is connected with the hex keypad, and after the value taken from the slave, this value is sent to the microcontroller, which is which is interfaced with the over LCD. I had already uploaded the hex file of master here and slave here, and now I'm running the simulation. When I press 7, it is then passing to this microcontroller, which is interfaced with this, and my results are shown in the LCD. And when I press 5, 5 will be shown on the LCD, and from here our contrast will be set, and all these things will not like that. Now moving towards the next part of lab 6, which is UART. In UART, we have universal asynchronous receiver or transmitter. From the name itself, it is clear that it is asynchronous. That means that data bits are not synchronized with the clock pulses, which we obtain from microcontroller. And these microcontrollers are interconnected, and this this hex keypad is connected with the over TX, and this T connected with this LCD. Now, underneath the simulation, in which I had already uploaded the code. This will show the value which I had pressed on of my hex keypad. And now moving towards its code. This is the code which I had uploaded on the microcontroller, which is connected with the LCD. In this, we had making the port D pin 0 as input and port B as output. In this, we had selected the baud rate value and in UBRR value. When our the baud rate is 9600, our UBRR value which we had calculated with the formula is 103. And these conditions are used to set the upper bits of the UBRR register, and this condition is used to set the lower bits of UBRR value. And with these conditions, we had enabling the reception and transmission of our microcontroller. And with this, we had stopped the bit selection on. And received data variable is used to store the received received data which we had actually received from the hex keypad, and then it will show it on LCD. This actually shows the this condition actually shows that it will wait here until the receivable buffer is empty, when it will become 0. And after that, if this condition is false, then it will not go to the loop and will break. And when it stays in this loop, it receives the value which will obtained in from UTR0, and LCD data write will show the received data. If I press 1, it will receive data as number 1, and LCD will show 1. And it is the code for TX. Previous code was for the microcontroller, which was connected for which was connected with LCD, and it is connected with the hex keypad. These are the values which can be given to the microcontroller, and these are actually stored in the microcontroller. When we press 7, it will pass its value to the microcontroller, and then from here it will go to the LCD. In this first half of code, we as initialized as input, and the other half is initialized as output. And this pin B value is stored in X, and if X is not equal to 0x 0f, then it will break. And if it is equals to 0xef, X will be equals to pin B, and if X is not equal to 0xef, it will actually compare value and search for the key pressed, and then its value will be going to the LCD. Now moving towards our next lab, which is lab 7. and this will learn about the external or PC interrupts in 80 mega 328p. Basically, the first type of device interrupts are called external interrupts, and these interrupts are basically called on a given status change on the int and pin. This is essentially an input interrupt and is great to use for applications when we might need to react quickly to an outside source, such as a bumper of a robot hitting the wall or to detect a blown fuse. So our first task is to show when you press button 1, it will show interrupt 1 is called, and when we press another button, which is button 2, then the LCD will show the uh, interrupt 0 call. I had already uploaded my hex file in this microcontroller, and here press button command is shown, and when I press button 1, interrupt 1 is called is shown, and when I press button 2, it will show interrupt 0 call. And this is the main task in lab 7. Now moving towards my next my code. In this, different types of built-in header files are used, where APR interrupt is one of them, and input output dot h is also one of them. And LCD dot h is if to use the LCD mm, mm, to write commands in to display the commands on the LCD which we had given to the microcontroller. From here, our int count is equals to 0. We had initialized the int count, and in our main we had connected. We had shown that DDRB, which is over port B. It is taken as output, and DDRC is also taken as output, and DDRD direction resistor port B is equals to 00, which is taken as input. Now these are the values. These are the conditions which are required for the for external interrupts of or PC, and where EICRA is an external interrupt control register A, and IMASK is external interrupt mask register, and here we had used LCD command 0x01, which is used to display the word hello. And then in our main function, we had actually in this interrupt function, where in zero vector is called, our button pressed is shown, and when we press a single button, it will show interrupt 0 is called, and when another button is pressed, it will show interrupt 1 is called. And in this lab, we had just to see that what are the results when we write the code in 80 mega of external interrupts, and different results obtained from this, and we had also studied about the external interrupts and its different types of registers which will store its value, and which will uh, now move towards our next lab, which is lab number 8. In this, we have interfaced the analog sensor LM35 with digital converter, which is uh, in this we have used an LCD as a digital converter. In this lab, when an analog signal coming from a sensor, it will then convert it from microcontroller. It will then convert it into digital signal, which will be shown on the LCD. And in this lab, we had seen that how a sensor can be interfaced with the LCD, and how it all works. In this lab, we had worked on the ADC converters, which converts an analog input voltage but then the digital value to successive approximation. The minimum value represents ground, and the maximum value represents the voltage on the AREF in 1 LSB. So This is a circuit simulation for over a task, and this shows the temperature value and temperature when our sensor sends the temperature, and it is the code for our task number 8. First, we have used the header files, and then we have defined the enable and register selection pins, and then for the LCD we had to use the sender command, sender correct, and sender string functions to send different values to the LCD. Here port B is used as an output, and port C as the input. Again port D is used as the output, and then there is a delay of 50 milliseconds, and these are the commands which are these are the registers which we had used, where AD is a register which is used which is these conditions are used to analog input channel is selected by writing to the mux and to the mux bits and add mux. Any ATC input pins as well as ground and a fixed voltage reference can be selected as single ended inputs into the ADC. In this step, the ADC generates the ADC is enabled by setting the ADC enable pin. Now these are the conditions which are used to enable these registers, and count initialize as 0, and these are the commands to clear screen, to left shift to right shift the cursor, and these are the conditions to take the temperature and write its value and display it on LCD, and through the send a command where uh, data is sending to LCD through our sensor. Now moving towards our next task, which is the duty cycle, to check the duty cycle. In this, our first task, our task is to check the variation of the LED glow when over the duty cycle is 100 and when it is 30. Mm, so uh, I had set the condition when my switch is off. When the switch is closed, this LED will be mm, so high all the time, and when the switch is open, that means the duty cycle is 30. And there is some link in this LED. I have already uploaded the code in this microcontroller. Yes, this is the 100 duty cycle when there is no change in frequency, and when the duty cycle is 30, there is some change in the frequency. There are high and low low signals. Moving towards its code, in this first crystal frequency is defined, and then different libraries are included, and in this global variable duty cycle is initializing as 0, and in our main program our PD6 is set as an output for LED, and for the PB for PB3 our input has been taken, and these are the registers to setting bits high in TCCR0 register for fast PWM mode, where PWM stand for wave generation registers, and in this command interrupt setting is enabled in time mass register, and in this condition we have set prescaler mode, and through this condition we have seen that when our switch is on, over OCR0A is equals to 250. That means it shows high value and continuously. And if this condition is not true, then over OCR0A, which shows the duty cycle, it will then uh, change to 30. So it is end of our microcontroller lab. Now moving towards our FPGA, which stands for field programmable gate arrays. Now moving towards that portion.
So this is our first step of FPGA, in which we have performed arithmetic test on quarters 2, quarters 13 software, and after writing the code, we had done the compilation. And this successful compilation will generate its waveforms. Now this is the waveform which we had produced through the arithmetic operations of plus, minus, multiplication, division. Now we can also see their bitwise configuration from here. We can also make riff table from here easily. And now moving towards our next task. Now moving towards our next task, which is the 4 to 1 multiplexer, in which there are 4 inputs and only one output. So it is a gate level implementation of 4 to 1 mux. And this is our code. Uh, we have to make sure that over this name demux, which is next to module, is same as the file which we had generated. And now we have created its waveform. We are assigning a different number of periods. Now running our simulation to generate its waveform. So it is a waveform which we had generated after the 4 to 1 after the code of 4 to 1 multiplexer. We can also create its circuit by article viewer. So there is a circuit for the article viewer in which we have used AND gates, NAND gates, and XOR gates.